I want to welcome everyone to season 2 of the Future of Energy podcast. It's sponsored by the Oshagi Center for Energy Transition at the Viterbi School of Engineering at the University of Southern California. In season 1, we kind of focused on the theme of energy transition, but I think that the more we learn and the more our experts are telling us that there are so many interesting new variables, from changing technology to more a better understanding of the climate, and to a lot of different discussions about what works and maybe what doesn't work. That we want to kind of change our theme on our podcast as well to the future of energy, because there is so much that is open and so much that to look forward to. There are challenges, but there's a lot to be optimistic about. If you're new to this program, we try to cover the vast size and complexity of the energy system by interviewing experts in a wide array of fields in an informal conversational format, using Mila and Roshan, our student co-hosts, to do most of the interviews. This season we have uh, Mila and Roshan with us, and we're going to get their perspectives on the reaction from the next generation of an energy workforce with regard to some of these themes as they come up. Our first topic is climate modeling. We frequently hear a lot about the results of those models in terms of average global temperature forecast. But how do climate scientists really develop these models? In this episode, we talked to Dr. Stephen Koonin from the Hoover Institute at Stanford University and author of the book Unsettled. And we get a look behind the scenes in our episode titled All Models Are Wrong, but Some Are Useful, a detailed look at climate modeling and models. Stay tuned.
Well, thank you so much, Dr. Koonin, for joining us on this podcast. We're very excited to talk to you today. Dr. Koonin, can you tell us a little bit about your career, your current role in the Hoover Institute at Stanford University, and how you became involved in global energy policy?
Sure. I got my PhD um, just about 50 years ago from MIT. Before that, I was an undergrad at Caltech, and before that, I grew up in New York City in middle-class family, New York City public schools. And my degree was in theoretical physics, which, as one of my elders said, is a license to poke your nose into anybody's business. And it's a great tradition among theoretical physicists to do that. I spent about 20 years on the Caltech faculty as a professor, doing work in nuclear physics and many-body physics, developing computational methods to handle many-body systems. And then got exposed through some government work to climate issues, both the modeling, the observations, and so on. That was just about in the early 90s. I took a detour and served for 9 years as provost at Caltech, so learned how to run a big organization, which was eye-opening. And then about 2004, I was getting a little bit bored with having done that for 9 years. And I got approached by BP, the oil company, to come be chief scientist. And I said, I don't know anything about energy other than it's conserved, which is what physicists know, of course. And they said, don't worry, you'll learn. They needed somebody to help them figure out what beyond petroleum meant. And for about 2 of those 5 years, I like to say I was the world's highest paid graduate student. I learned all about energy, the energy business, the oil and gas business, about alternatives and renewables. I picked up the family and moved from Southern California to London. And it was a real eye-opener. Not only the private sector, not only the international scene, but energy. And I spent 5 years doing that, helping the company figure out its strategy for technologies as the world was starting to talk about carbon. And then my friend, colleague, Steve Chu, who was at Berkeley at the time, I believe. Um, no, maybe he was at Stanford already. Became Secretary of Energy in the first Obama administration. And he said, come help out. And so I did. I served for 2.5 years in the Department of Energy as Undersecretary for Science, again, helping the department plot its investment strategy in new energy technologies, and also helping out generally. I mean, I had learned about nuclear security matters um, earlier in my career, so generally helping out as kind of chief scientist for the department. And then after 2.5 years, that's plenty of time in a Senate confirmed position. If you look at the average, it's about a year and a half. I went to NYU and started a center about big data for big cities, and did that for 6 years. There's a master's program and a lot of research that still exists from that. I stepped down after about 6 years and focused again on climate and energy, wrote a book, Unsettled, that we've sold about 200,000 copies. It tries to really just lay out the climate science issues for general readership. And then starting in September, so just about 2 months ago, I took up a full-time position as a senior fellow at Hoover, where which is an institution at Stanford. Much more multidisciplinary than other places I've been. A good mix of economists, political scientists, former military, social scientists of all kinds, and a few scientists and engineers. And it focuses on policy issues, which is kind of a natural evolution of the kind of roles I've been playing. So, in a nutshell, that's a little bit about how I came to be what I am.
That's incredible. And serving as the Undersecretary of Science in the Department of U.S. Energy under President Obama, could you describe more what was that job like?
So I, by virtue of the org chart, I had little direct responsibility for organizations and had the ability to think out of the box about what the department was doing. So the Department of Energy is particularly broad. I mean, part of it is certainly about energy, but part of it also is about basic science. It's the biggest funder of basic research in the government. Another part of it is about nuclear security, which is, again, the numbers change over the years, but was a big part of the program, the National Laboratories, the Nuclear Weapons Stockpile, non-proliferation. And then another part is about cleanup. There are contaminated sites from nuclear weapons activities, and the department is involved in cleaning it up. So it was really interesting spectrum of activities, many of which I had been exposed to before. But also, what was eye-opening is, first of all, how good the senior civil service is. The folks who are the senior government employees who stay there for a long time are just really dedicated and very good. So my respect for them increased enormously. And then I think the second is how difficult it is to actually get anything done. There's so much coordination that goes on across the executive branch, with the White House, the other agencies, with the legislature, of course, Congress. And as my chief of staff used to remind me, the Constitution is constructed so that the government moves slowly, except in time of crisis. So you're really laying the groundwork for things that will happen long after you're gone. And in fact, many things did happen like that after I left.
Incredible. Thank you.
Thank you. And so when you were talking about your past, you mentioned that you wrote your book Unsettled, which is a really famous book on climate modeling. This may be like a dumb question, but I was wondering what the difference was between climate modeling and weather forecasting.
Oh boy, there's a big difference. And in fact, if we go back beyond the modeling just to the phenomena, weather is kind of what happens every day or every week, whereas climate is the long-term statistical properties of weather. Typically, over decades, the standard definition by the World Meteorological Organization is 30 years. So you need 30 years of weather data, the statistical properties of it, the averages, the variances, the extremes, and so on, to define a climate. When we try to model the system, the task of weather modeling is very different than the task of climate. They're the same equations in the end, right? It's conservation of whatever, mass, energy, momentum, and so on. But the way in which you apply those is very different. Weather is really an initial value problem. Here's the state of the atmosphere today: winds, temperature, humidity, pressure. And now tell me what it's going to be like over the next hour, over the next day, over the next week. Weather forecasting runs out after about a week because the system's chaotic, and even small changes in how you start can lead to big changes in your predictions 10 days out. So we see weather forecasts going out only 10 days. And it's better than it used to be, but it's still very different than trying to predict the statistical properties of weather over several decades or a century. The climate problem, it hardly matters how you start the climate system because the atmosphere forgets after 2 weeks. And it's more of a boundary value problem. I mean, there are energy coming in, energy going out. The oceans are kind of the long-term memory of the system. So oceans are important in climate, ocean dynamics, but the oceans are not so important in weather. They're just kind of fixed boundary conditions on the weather equations. So there is a big difference. Some people try to use the weather models to predict climate, but the important thing is to have the ocean dynamics, which are generally ignored in the weather models because they take much longer time, but are very important in climate.
I would think it would be the other way around. They would try to use the climate model to imply the weather, maybe the weather forecast.
Good. So now we get into the details a little bit of the modeling. The climate models have to cover the whole globe, and they have to do it for many time steps. Typical time step is 10 minutes. You want to run it for a couple centuries. So that's a big computational burden. Whereas the weather, what that computational burden means is that the grid boxes in the climate models can't be too fine. Otherwise, there are too many of them. And so state of the art right now is a grid box is 100 kilometers on a side. That means, there's probably one grid box over the whole LA basin. So it's not very good. The weather models, you don't have to run for such a long time. And so you can have kilometer size grid boxes. And so you can't take the climate models and run them for weather because the description is too coarse. And you can't run the weather models long enough to get climate because they run too slowly. They got so many grid boxes. So again, the technologies are the same. There is one center that tries to use the same model for both, but in general, they're really quite distinct problems.
Okay. And so when you get these models, how would you explain this to the general public? Like, how would you tell this story? This is what's happening. How would you explain? Because I imagine this is very difficult to explain, right, at a high level. How would you explain this to the people today?
Yeah, so let me try. And I don't want to try to explain the technologies, right? Not necessarily the results. So we cut the atmosphere into some number of voxels, namely grid boxes, that, as I said, currently are about 100 kilometers on a side and maybe go up 20 layers in the atmosphere. And then we do the same in the ocean, finer grid boxes, perhaps, because the properties of water flow, and layers down into depth as well. When you
layers, what do you mean by layers?
Oh, so we have to describe not just the atmosphere at the surface, but we have to build up a stack of boxes.
Okay.
Okay. And it turns out those layers are very thin. So the scale height of the atmosphere, the characteristic scale, is about 8 kilometers, whereas the grid box size is 100 kilometers. And so if you want to put, let's say, 5 layers within the 8 kilometers, you've got very thin grid boxes stacked up. And that makes a lot of trouble when you try to do the fluid dynamics. So anyway, we cover the box, and we cover the Earth, atmosphere, ocean with 10 million voxels. And now we're going to write down the basic physics laws, conservation of mass, momentum, energy, humidity, and so on, discretize them on these boxes, and let the equations run. The problem is, one of the problems, there's several, but one of the problems is that there are lots of things in the atmosphere that happen on finer scales than the grid boxes. And so if you look behind me in my image, you can see clouds. The clouds might be a couple 100 meters across, or maybe a kilometer. You can't describe that kind of detail in the computer model with boxes that are 100 kilometers on the side. And so you have to make assumptions about what happens at the so-called subgrid scale, given the temperature, humidity, insulation in a grid box. How many clouds are there? What fraction of the box do they cover? Because that's important in reflecting sunlight. So there are several kinds of subgrid parameterizations. People try to do the best job they can in making them, but different people do it in different ways, and so the models give different results. And so there are, 40 different models around the world, maybe 50. They all give different results because of the way they're constructed, and they're all a priori plausible. There's sensible people who've tried to build them. So one of the problems is that there is no one model. Multiple models give multiple results, and many of them do not agree with what we have seen in observations over the last 100 years.
I imagine with all these computations to forecast and all that. And I know with AI, a new thing is like climate modeling, right? With more computational power.
Right.
I think that would be a huge impact on the energy sector as well, right? When we're talking about the energy transition, we're talking about, with Microsoft getting a new data centers and stuff like that. This is probably a huge computational load, right? Energy.
Right. So yeah. So people are. Let's talk about the climate side first, and we can just say what about the energy side. On the climate side, people are using machine learning, more generally, or AI, in two different ways. One is to do a better job on these subgrid parameterizations. And then the second is to do the whole problem with AI rather than with the typical discrete partial differential equations. There's been some fast success already. People have published papers on weather forecasting, where you feed into it the map at a given time, winds, pressure, humidity, and then you ask it to predict the map an hour later. And you can train up the net to do that. And it actually does quite a good job, much more efficiently than the usual ways of weather forecasting.
That's nice to hear, at least.
Yeah. In the end, it's reduced to image understanding, as most of these problems are. Right? And the application to climate in a more conventional way, the subgrid, I think is yet to be demonstrated. Right? People are working on that. On the energy side, there are so many problems that demand optimization, just dispatch of generating resources on the grid, for example. When do I turn on whatever? Because that's connected not only with the physical system, but the market as well. There are electricity markets. So, I'm sure that we will see progress and improvements as a result of applying AI to energy problems.
Thank you.
And if you look at the geological history, the Earth has been heating and cooling in different ways long before humans have had any influence. What is the baseline for current models, and how how is that important in understanding current trends?
So conventionally, we refer to the temperature, at least, at the so-called pre-industrial time, about mid-18th century, 1750, which was long before human influences became significant enough to affect the climate. CO2, other greenhouse gases, have not built up. Of course, you can ask, how do you know what the temperature was in 1750? And we have proxies, tree rings, weather records. They're spotty, but they give us a sense of what the temperature was like. Of course, as you get into the latter 18th century, 19th century, the record gets significantly better. We're pretty sure that the globe has warmed 1.1, 1.2 degrees Celsius since the mid-19th century, and the warming continues today.
And what is the range of global mean temperature predictions? And how do the P90 and P10 outcomes change life on Earth in 50 or 100 years? And could you also explain to our audience what P90 and P10 outcomes are?
Right. So as we try to, let me just do a digression for a moment and explain a little bit of climate terminology.
Please.
When we say a prediction, we say that the global temperature will be 1.6 degrees at the end of this century, higher, 1.6 degrees higher. So it's a definite statement about some future condition. We can also talk about a forecast, which is a probabilistic prediction. Namely, the average temperature rise at the end of the century would be 1.6 degrees, let's say, but it could range from 1.2 to 2.0 with some distribution. So that's what's called a forecast. And then there is a projection, which is a forecast conditional on human activities. So if emissions continue to increase at some value, then we forecast that the temperature would be such and such probability distribution. So it's good to try to be a little bit precise about how one talks about these things. So, of course, if we go to, let's say, the end of this century, so 80 years from now, what the temperature rise will be depends upon at least two things. One is just how much emission will there be between now and the end of the century? Not only CO2, but methane and aerosols, which are a cooling influence. And then second, what model are you going to use? Because we don't necessarily know what the best model is, we take an average over 40 different models and have some kind of probability distribution. So projections of the temperature rise at the end of the century range from 1.1 or 1.2 degrees up to 5.5 degrees or so. I won't get the numbers exactly right, but 1 plus up to 5 plus. And of course, those are very different outcomes, which right now we really don't know what we can say. At the P10 level, it means that there's a 10% probability that it would be less than that. And at the P90 level, is a 90% probability that it's less than that. So those define kind of the outer limits of what we might expect. And if it goes up, we've already seen 1.1 or 1.2 degrees. So, if the temperature at the end of the century turns out to be the same number, it's not going to be any different than what we've seen now. If, on the other hand, it goes up to 5 degrees in the most extreme scenarios and the most sensitive models, then that's a very different world. And we will see changes, probably faster sea level rise, more heat waves, at the gross level, that's what you would expect.
When you're talking about the temperature changing, do you think the burning of fossil fuels is a major reason?
I think that I'd like to say human influences, of which accumulating CO2 from fossil fuel burning is probably the major influence. Human influences, I would say, account for at least half of the rise. But whether it's all of the rise or half, I don't know. There is significant natural variability in the system, and untangling that from the so-called forced variability is a major research problem, and I don't think we have that down yet. And one should also note that the global temperature is just one number that purporting to describe everywhere on the globe and all phenomena. There are many other measures of climate that we need to respect: precipitation, storms, cloudiness, sea level rise, drought, floods, and so on. And what perhaps surprises people a lot is if you go to the most recent UN report and look in table 12.12 of Working Group 1, it lists about 40 different weather phenomena. And for almost all of them, it says there's been no observable trend over the last many decades. So no detectable increase in hurricane or tropical cyclone activity, droughts, floods, et cetera, et cetera. So, we have not yet seen, and maybe never will see, significant changes in those weather phenomena, which in the end are what matter for human civilization.
Is increasing the concentration of CO2 all bad? Is there no upside to it? Is there no balance at all?
Well, of course, none of the media want to talk about the upsides, but there has been an observable significant greening of the earth. We see vegetation in regions where we've not seen it before, edges of the Sahara Desert, elsewhere. And it's a lot. If I remember right, it's something like 40% increase over 40 years. And even NASA, the US government agency, says a lot of this is due to CO2. Plants love CO2. The current atmospheric concentration is about 420 parts per million of CO2. In greenhouses, we pump CO2 in to make the plants grow better. It gets up above 1,000.
Wow.
And the plants love it. So, we've seen crop yields go up a lot. The CO2 does two things. One is it makes the plants water efficient. They don't have to open up their stomata as much to get CO2. They can retain more of the water. The second thing is the warming of the planet, certainly associated with CO2, extends the growing season. And so we've seen crop yields just go up and up and up. So that's at least one good thing. Another good thing, which people don't like to talk about, associated with the warming, presumably due in large part to CO2, is that the warming is not uniform. What we see is that the cold temperatures go up more than the warm temperatures do. And so cold nights have become mild. Cold winters have become more mild. And if you look, sorry?
Why is that? Why is it so that, why is there a disparity in changing?
It's got to do with how the CO2 affects the radiation. I mean, the blanket is still operative at night, and so it keeps things warmer than it would have otherwise. And when you look at deaths around the world, fatalities due to extreme temperatures, it turns out that there are 9 times or 10 times as many people who die from extreme cold than from extreme heat. And so as the cold temperatures have warmed faster than the hot temperatures, there are fewer people dying from extreme temperatures as a result of the globe warming up, right?
That's interesting, yeah.
Yeah, you would never see that in the media.
Yeah.
And in fact, part of the problem with this whole business is it gets misrepresented. So if you go to the summary of the most recent IPCC report, It's got one sentence about deaths from extreme temperatures, and it says heat waves are on the rise and they're contributing to fatalities.
But
But
doesn't
it doesn't say a word about the lower deaths at extreme cold temperatures.
that's it.
Yeah, they're trying to persuade you rather than inform you,
Yeah.
which is a generic problem in this business.
Yeah, so there are many groups involved with climate modeling, each in their own methodologies. How are these results combined? And are there any models that are better than others in predicting climate change?
Yeah, so the most naive way to combine them, which is what's often done, is to just average the results for whatever climate variable you're looking at. Or if you're a little bit more careful, you'll look at the distribution of results, giving them equal weight. You can try to do a little bit better. For example, one gross measure of the model performance is to look at what's called the climate sensitivity of the model, which is phrased as how much would the surface temperature go up if you doubled CO2 from 280, the pre-industrial value, to 560 parts per million. And the models give a range of those. It goes from about 1.5 degrees Celsius. Turns out to be the Russian model is the least sensitive, up to something like 5 or 5.5. And in the most recent IPCC report, credit to the authors, they said about 40% of the models were too sensitive to be believable. And so they say those results should be disregarded, which is interesting. They previously had practiced model democracy. Diplomatically, you couldn't say one model was better than the other. But beyond that kind of gross number, when you look in detail, how much change in rainfall will there be in the Great Plains, or how much of a change in the monsoon will there be? The models tend to be all over the place. And when you get down to that kind of regional level, even the experts say they're not very useful at all. And so as we think about adaptation, how should we respond to a changing climate? They're not of much use right now. There's a big push in the modeling community to get even faster and more powerful computers. They want a world center for modeling computation. But in fact, it's not obvious, given all the knobs that there are to turn and all the discrepancies or differences among the models. It's not obvious that a more powerful computer is going to help.
And are these models accessible to be interrogated in their methods?
Yeah.
Could you further
Yes.
explain that?
Almost all of them make their codes available. I mean, they're very complicated, as you would expect. But maybe more usefully, the outputs are archived, grid box by grid box and week by week or whatever. And so you can go in and construct your own metrics of the various models and look at how they differ among themselves. So yeah, I mean, there's a concerted effort which was started already in the 90s. The US program is called PCMDI. It's run out of Livermore, or at least it was, Program for Climate Model Diagnosis and Intercomparison. And the modeling community has a standard set of problems, exercises that it does so that you can make a meaningful comparison between the results of different models.
And just a follow-up question on that. You mentioned climate sensitivity, and with these models being accessible to a lot of the community in modeling, how can we understand and how can we know kind of in reality where we are within the range?
We can't, okay? I mean, in part because the human influences have not been strong enough yet to clearly drive the models out of the range of natural variability. And so we have no good answer yet for what the climate sensitivity is. I think the IPCC, if I remember right, it says it's between 2 and 4 or 4.5. Again, I haven't looked at these numbers in a while, so somewhere between that, which is a range that's less than it was, say, 5 or 6 years ago, but is still not very comforting. Those are 10 to 90% numbers. So if we wait a while longer, a couple decades, we can expect that the warming will come out of the noise and we'll be able to get a better sense of what the sensitivity is.
Thank you.
And just to go back to your book, Unsettled, again, the famous environmental scientist Vaclav Smil, I'm not sure if I'm saying the name right, but
Right.
the quote is, "We have too many global warming books, but this one is needed. Stephen Koonin has the credentials, expertise, and experience to ask the right questions and to give realistic answers." For our audience, what are the questions we should be asking, and how do we tell if we're getting realistic answers?
Oh boy. I think the questions we want to ask, kind of the bottom line question is, as the climate's changing, what impact is that going to have on ecosystems and, more importantly, on society? How should society respond to the circumstance of growing human influences on the climate? And when you ask that question, how should, it's not just, oh my God, we're changing the climate. But let's say, for example, 6 billion people need more energy on the planet, the people at the lower end of the poverty spectrum. And how do we get those folks energy? And how do you balance that trade against the desire to reduce human influences? I think that is the big question. And it's not a science question. It's a kind of values question. It is, how do I weight? What risk tolerance do I have? How do I weight development and economic well-being against the environment? How do I balance north-south equities, intergenerational equities? That's the discussion we should be having. And it's rare to see that discussion because it's so difficult. I listen to lots of debates about decarbonization in the developed world, in the US, or Europe, Japan. And I always like to ask, when I get a chance, what are you going to do about 6 billion people who are energy starved? And
Yeah.
if you eschew fossil fuels, you've made it more difficult, more expensive for them to get that energy. Nobody has a good answer for that.
And I think with the changing climate, you talked about how, less extreme cold weather is a benefit, but are there any other benefits to the changing climate?
Well, so I think we have kind of three measures or ways of trying to answer that question. The one I like the most is, let's look at the period from 1900 until now, about 120 years. During that time, the globe warmed 1.2 degrees, and we expect about the same amount of warming, a little bit more by the end of the century, over about the same period of time. And since 1900, we've seen the greatest improvement in human well-being ever, despite, or some people might say because of, the warming. And you look at it, the lifespan went from 32 years to 72 years on average. The GDP per capita in constant dollars went up by a factor of 7. The literacy rate went from 20% to 80%. And maybe most interestingly, the death rate from extreme weather has gone down by a factor of 50 because we got better at predicting storms and more resilient to floods and all that sort of thing. So to think that another 1.2 degrees is going to significantly derail this just beggars belief, in my point of view. The second thing you can try to look at to answer the question is, you can look at the loss rates from weather events, extreme weather events, over the last 30 years. And both nationally and globally, the economic losses average about 0.2%, 0.3% of GDP. And they haven't been changing. In fact, it's slightly down over the last 30 years. So again, a signal that whatever is happening with the climate over the recent decades, society has been doing quite well. And the third is that, of course, people try to project what the effect of increased temperatures is going to be over the next 100 years. And by far, the consensus in the research literature, and even in a paper put out by the Biden administration a year and a half ago, is that warming of a few degrees is a few percent impact on the GDP. That's not a few percent on the rate, it's a few percent on the GDP itself. So that by 2100, the GDP might be 2% smaller than it would have been otherwise, but it would have grown by a factor of 3 or 4 over the next 80 years. So, everything suggests that we will be able to adapt, manage quite well to the gradual and modest warming that the models project. Of course, you could always say, you never know what's going to happen in the future, and there are tipping points and so on. But the models don't show that sort of thing. And there are disparities. The wealthier nations will be able to do better than the poor nations. That's true. We should try to deal with that, but we've already had to deal with that circumstance not very well, actually. So anyway, that's a little bit about what people believe the effect will be of increased warming.
Thank you.
Perfect. And I kind of wanted to follow up on that. With all of the research and information and ranges of modeling and climate sensitivity, how can scientists tell a realistic story about their studies in today's information overload and misinformation environment?
Yeah, it's really tough. You're not. I mean, one of the reasons I decided to speak out first in op-eds and then write the book and continuing to do public information is because there's demonstrable misrepresentation in the IPCC reports, the UN reports, and in the US government reports. You can see that just by reading the summaries and then looking in the back of the report where it says something very different. Or sometimes a report says something and the data actually say something else. And I think it's the job of scientists and scientific institutions to paint a transparent, balanced, unbiased, and complete picture of what we know and what we don't know. And have not been getting that. Right? So, again, to take a recent example, we've had some terrible flooding as a result of hurricanes in the Southeast over the last month or so. And unprecedented. But you can find pictures of Asheville, North Carolina from 1916, so 100 and some odd years ago, that look just as bad as the ones that you take today, that just as much rainfall. So, we need to be cognizant of the past. Whenever I hear, record unprecedented, my inclination is always go look up the weather records over the last century and see how unprecedented is this really, and you rarely find out that it's unprecedented. So that's one sort of simple way. A second is look at multiple sources. I mean, I like to, at least for news coverage, I look at the New York Times, I look at the Wall Street Journal, and they sometimes tell very different stories about climate. And of course, if you're capable as a scientist, you can go read the literature. So, for example, islands in the South Pacific are actually growing in area despite rising sea level because coral grows and adds more area to the island even as sea level goes up. You can find that in research papers. Very rarely will you see that in the popular media. And then I think you got to read widely and look at the numbers. It's so easy for the general media to talk about climate in absence of numbers or historical context. And that's what I look for when I read the popular coverage.
Thank you so much. Roshan, I'm not sure if there was any other questions you wanted to ask before we wrap up.
Well, I had a short question about the coral thing, but is that habitable land? Is that coral like?
Eventually, it will be. I mean, the whole island, a lot of it, the atolls, was not habitable at the beginning, but it gets to be as the centuries wear on.
That's pretty interesting, actually.
Yeah, yeah. Right. I mean, again, I can't remember the exact names of the islands, but you can look up people, the way in which it's done is from aerial photography. They have pictures from the 50s, let's say, and they can compare them over the decades, and you can see it's actually going up. So, another great misconception is the rate of sea level rise. There are tide gauges around the coast of the US and internationally. Here in New York, in the New York City area, there's been a tide gauge at the southern tip of Manhattan, the Battery, as it's called, for about 160 or 170 years. And, it's a pretty good straight line at a foot a century. So the sea level on average going up a foot a century. The city's certainly been able to adapt to that very well. And it's about the same number on average around the coast of the US, but of course there's some regional variation. And the sea is not about to leap up and claim more land. Yes, there are storms that come up, but the fact that the sea level is half a foot higher than it was 50 years ago doesn't make the storms all that much worse when the storm surge is 10 feet or something like that. So we're not about to be inundated. You do find people living in places they probably shouldn't be living. Right? Here, Rockaway, in the middle of forests that are going to burn eventually. Paradise, Maui, there were warnings. There were reports written. Katrina, there were reports written. The power problems in Houston a couple winters ago when Texas more generally. That happened 10 years ago and it happened 20 years ago. And there were reports that said you should do X, Y, and Z to prepare. And we don't do it. So at the very least, we say you should at least prepare for the past. And we don't do that.
Well, Dr. Hoonan, thank you so much for your time today. It's been a real honor to have you on the podcast. But before we leave, is there anything we forgot to ask you that's important to share with our audience?
I would say there is no climate crisis. Yes, there's an issue here. There's a problem. But it needs to be dealt with if we're going to do it through the energy transition. We need to do that gracefully and thoughtfully. If you try to transition too fast, it's going to be disruptive. And, many people, at least in the developed world, have come to believe this is the most important problem. And it would be good if they could learn about the rest of the world and what some of the other problems are that say, well, maybe you don't or shouldn't go so fast in this energy transition.
Thank you.
Thank you.
All right. Okay.
It was great talking to you.
Right. Good conversation.
Dr. Kudic for the senior staff of the DOE often gets a lot of criticism from the outside, but his experience shows us that most DOE employees are really dedicated. They do a great job with their responsibilities.
Yeah, absolutely. And if we recap a little on what we discussed in this episode, I think it's important to highlight just exactly how much data we're dealing with in the case of, weather mapping and weather planning. Like in the latest UN report, it states that many of the weather phenomena, there's been no observable change due to climate change over the past 30 years. And so 40% of those models produced were not believable, as stated in the episode.
Well, again, it is also very difficult to get anything done with given all the kind of coordination kind of needed with the other agencies. The Constitution is made so the government moves very slowly, so that especially in the time of a national emergency, because there's just so much matters they have to take into account, right? There's so many agencies.
Yeah, I mean, as we heard, it takes weather data to be able to define climate. And so what was stated, the atmosphere forgets after 2 weeks, so it doesn't matter how you start a climate model, but the ocean has a long-term memory. I thought that was a very interesting perspective into it because, again, we're dealing with such a large quantity of exact accurate can it be, especially in previous years. But now that we have new technologies emerging into the scene, it rather than climate modeling becoming a boundary problem, we see that weather modeling is an initial value problem. So as the technology develops, as we heard during this episode, it's going to be very interesting to see the accuracies of where weather modeling can go.
Absolutely. Clouds are incredibly more detailed than what you can define in climate grids, right? 40 to 50 different models will get different results. And people with different assumptions have different interpretations, and results just don't agree sometimes.
I think the one line that from Dr. Kunin that really stuck with me was, trying to understand the past as well as a starting point for these models. And they said we should at least prepare for the past. And unfortunately, right now, we're not even doing that.
In episode 2, we are going to talk to Arthur Lee to get an understanding of how global organizations, like the United Nations Framework Convention on Climate Change, work to build consensus agreements, like the Paris Accord in 2015, and on what actions to take about our energy systems. Can you believe that we have just seen the 29th annual meeting of the UNFCCC in November in Baku, Azerbaijan?
Well, our leaders have been talking about climate change for longer than we've been alive, right? This is another signal of how complex and large this conversation is. Countries and companies have spent trillions of dollars to increase renewable energy supply and to change the way that we think about energy. Our global energy systems are so complex, or I mean, I should call them systems. And the story of the energy transition is as fascinating as it is complicated. These are huge issues, but it's a good way to start our program.
Um, exactly. I started in 1999 when I realized that wow, there's this thing called a Kyoto Protocol. Obviously, that was one of the initial questions. What is this Kyoto Protocol? What's greenhouse gas management? What's Kyoto Protocol? So it was because of the Kyoto Protocol that Indonesia started thinking about replanting forests, some of the forest that has been deforested, especially around our operations that we had no control over. It was all deforested by the people who live there, who conducting the slash and burn agriculture because they needed to make a living. There's some of these folks, they're not necessarily the landowners, but if they own the land whether or not they did, simply they carried out slash and burn. You cut down the trees and then you start planting, and you burn the trees, and you start planting so that you can feed your families. So that got me then into the whole world of okay, if one country can do that, and the pollution, not only the criteria, health criteria, air pollutants, but also CO2 is global. Okay, what's next, right? So it's all about the global treaty. Towards around this time of year, November, early December, there's always in the news, oh, countries are getting back together, and you would wonder, why the heck are these countries always coming back together every year? Don't they already have a Paris Agreement? Well, yes, they do, but the Paris Agreement is only, again, like around 40 pages, and they're now writing hundreds of pages of regulations, so to speak. And each of these provisions in the regulation have to be agreed to by each country. Okay, can you imagine that? There's no and there's no voting. Okay, I'll add another wrinkle onto that. There's no voting.
How does it
So
get agreed?
yeah, the IPCC was awarded the Nobel Peace Prize. I thought to myself, oh my God, this is really a surprise. In fact, it was quite a shock that the organization itself got a prize, and it was shared. Of course, the prize was shared with former Vice President Al Gore, uh, who actually famously flew to Kyoto in 1997 to clinch that deal on the Kyoto Protocol. That's an aside, okay? But but the IPCC shared the Nobel Peace Prize with former Vice President Gore. And I was just shocked that people will recognize, but I didn't think too much of it afterwards. Not too much. And then the IPCC then sent 2 days later sent an email to all of us who participated in the IPCC and said, "You are all recognized," and it carried through that promise by actually sending us this huge certificate. The top half is actually is a replica of the Nobel Peace Prize 2007 itself. Okay, and the bottom half of this huge thing is says something about IPCC recognizes me, Arthur Lee, for contributing to the Nobel Peace Prize of 2007. So I was stunned to have received that as well, and it was great. Now, then that was 2007.
Thank you so much for joining us for the future of energy. Special thanks to each of our guests today and to our technical wizard, Abhi, for his important contributions to this episode. Don't forget to subscribe to our podcast so you can automatically get access to all our new episodes. You can find us on Apple, Spotify, YouTube, or wherever you get your podcasts.